Let us now discuss about magnetic coupling. So we know the Faraday's law. What is it? A time varying voltage is going to produce a voltage. It is going to induce a voltage. So V is equal to N times d phi by dt, where N is the number of coils. Okay, so we will be discussing more about the Faraday's law, Lenz's law, and the whole magnetic field that is produced because of a conductor. We will discuss more of it in the field theory as well as the machines. Okay, so for now you need to know that if you have a coil and a current is flowing through the coil, then it is going to produce a magnetic field like this. Okay, and the direction of magnetic field, it will depend on the sense of configuration. Okay, so that dot polarity we will discuss in networks itself. So now what is the voltage that is induced because of a time varying magnetic field? If you give a time varying field, then the corresponding magnetic field will also be time varying, right? So that will induce a voltage across this coil. Okay, so we also know that for an inductor, what is the voltage and current relation? V is equal to L di by dt. Okay, so from these two equations we can get an expression for the inductance in terms of the flux. So what will it be? V is equal to N d phi by dt, you can write as N d phi by di into di by dt. Okay, so di is the multiplication as well as the division term. So now if you compare this term and this relationship, you can see that the inductance you can write as N times d phi by di. So the voltage that is produced across the inductor is primarily because of the magnetic field that is produced. Okay, so now what happens? This is the self-inductance. This is self-inductance L. We call it as self-inductance because it is the magnetic field due to the current flowing in its own coil. Now the next term that we need to know is the mutual inductance. So what is mutual inductance is, you will be dealing with two coils here. So let us take this to be one coil and there is another coil like this. Okay, now let us say a current I is flowing through the first coil. Let us take this to be coil 1 and this to be coil 2. Now no current is flowing in the second coil. But what is going to happen? The current flowing through this is going to produce a magnetic field which is going to interact with the coils, with the turns in this coil. Now once this linking happens, then there is going to be a voltage that is produced across this second coil as well. Okay, so that parameter is what we call as the mutual inductance. So the procedure you can write, current I flows through coil 1. And because of this, a flux phi 1 is being produced. So we can take this current as I1 to represent coil 1. Okay, this produces magnetic flux phi 1. Okay, now phi 1 we can divide as phi 1 1 plus phi 1 2. So what is phi 1 1 and phi 1 2? The phi 1 1 is the flux linking only coil 1. And phi 1 2 is flux linking both the coils. Okay, only coil 2 will not exist, right? Because it is originating from coil 1. You can see that only some of the lines are associating with coil 2. Some of the lines, magnetic field lines, are not being associated with, they are not linking coil 2. Okay, so that whatever is not linking coil 2 we call as phi 1 1, and whatever is linking the coil 2 we call it as phi 1 2. Now this will induce voltage V1 across coil 1. And what will be that voltage? V1 is equal to N1 d phi 1 by dt. that is the number of turns in coil 1, into the d phi 1 by dt. Here we have taken the total flux, okay, because phi 11, phi 12 both are linking coil 1. So we are dealing with the total flux here, okay. So this is going to be equal to L1 di1 by dt. Now what is happening here? This induces a voltage V2 across coil 2. And what will be this expression? V2 will now be equal to the number of turns of that coil, that is N2, into d phi 12 by dt. So d phi 12 is the flux linking both the coils. That means only that part of the flux which is linking coil 2 we are taking here. So what will this be? This you can write as N2 d phi 12 by di into di by dt. So now this term N2 d phi 12 by di, this is what we term as the mutual inductance. And what is the, in contrast, what is the expression for L1? L1 is equal to N1 d phi 1 by di. That means the total flux we have here, okay. Here only the part of flux which is associating, which is linking coil 2. So the voltage that is produced across the second coil is equal to MD, this is I1, right? This is I1. MD I1 by dt. Now if you consider the other way round, that means now the coil 1 has no current flowing through it. In coil 2, there is a current I2 flowing. Then what will be the voltage that will be induced across coil 1 because of current I2? Here V1 is equal to M times d I2 by dt. Okay. So this mutual inductance and this mutual inductance both are same. They are equal in value. Okay. So if you want to differentiate, however, you can write this as M21 d I1 by dt. Okay. So M21 means the mutual inductance because of the current in coil 1. Now here you can write M12. Okay. So this is because of the mutual inductance because of the current in coil 2. But since both of them are same, M12 is equal to M21 is equal to, we can simply use the variable M. Okay. Now we will see what is dot convention. So this is very useful in deciding the polarity of the induced voltage. Okay. So till now we were taking two coils, but now we will take a magnetic core on which the two coils are bound. Okay. So what is the function of a magnetic core? It will help to better couple both of the coils. So we'll draw now, then you will understand. This is the first coil, let us say, and the second coil is like this on another leg of the magnetic core. Now what is going to happen if a current I passes through coil 1? So we will take this as coil 1 and this as coil 2. Okay. Now the magnetic field that will be produced because of this current I, it will be mostly confined to the magnetic core. Why is that the case? Because the magnetic core will have the more permeability. That means it will more easily allow the magnetic field lines to pass through it. Okay. So the magnetic field lines, they should actually be like this, but most of it, instead of passing through air, they will prefer passing through this low reluctance path. Low reluctance, or you can also say high permeability. Now the magnetic field direction we have drawn in the clockwise sense. So why is that? If you apply the right hand rule here, you can wound your fingers in the direction of the current flowing through the coil, so that your thumb is going to point in the direction of upward direction. Okay, so that means it will go like this and it will come back like this. We now have to find out the polarity of the voltage induced across this coil, because we are talking about the mutual inductance here. Okay, so now where will be the positive polarity? Where will be the negative polarity? We have seen the relation V is equal to n d phi by dt. This is only the magnitude, okay? But there's also the polarity also will be given, but that will be given by the Lenz's law. So according to Lenz's law, we have V is equal to minus n d phi by dt. So what does the negative sign signify? It signifies that the voltage will be induced in such a way that it will oppose the rate of change of flux. So that means if flux is increasing, then the voltage will be induced in such a way that flux will decrease. And if flux is decreasing, then voltage should be induced in such a way that flux will now increase. Using this relation, we will now see the polarity that is induced here. Okay. So if a current I is flowing, then it will be driven by some source. So we can draw the source here as well. Okay. So this is the positive polarity, meaning that during the positive half cycle, the current is flowing like this. So you can draw the sine function like this. This is for the current I. Okay. Now what is happening here? The current is increasing, right? So automatically the flux also will increase. So from 0 to pi by 2, what is going to happen? The flux that is linking this coil will increase. So the voltage should be induced in such a way that the flux is decreased. Okay. So when will the flux decrease? When the current flowing through this coil is in the opposite direction. It will produce its own flux which is in the opposite direction to this flux. That means the resultant flux should be in this upward direction, in the counterclockwise sense. Okay. So now you can point your right hand thumb in this direction. Then what is the direction of your fingers? They are being curled like this, right? So that means the current will be flowing like this. This direction of current will oppose the increase in this flux. Okay. So here you're going to have the current is going to come out of this terminal of this line. Okay. So now this is the induced voltage. That means this coil is now driving the current. So the current is now coming out from which polarity it should come out from? For a source, it will come out from the positive polarity. So you're going to write the positive polarity here. Okay. So we have been able to find out the positive polarity, right? Let us now consider another case. This is the primary coil. Now the secondary coil, instead of drawing over the coil like this, what we will do? We are going to draw like this. Okay. So you can see the difference here. This is different from this sense of winding. Sense of winding is now changing. Okay. So now for the same, now flux is increasing in the clockwise direction. Now what do we want? This coil to oppose that change. So once again, if you point your right hand thumb in the upward direction, then the direction in which your fingers will curl will give you the direction of current in coil. So this is the direction of current in coil. Now you can see that the current will now flow into the coil through this terminal. Here through this terminal the current is flowing out of the terminal, but here it is flowing into the terminal. The difference is because of the sense of winding. Now where will be the positive polarity? The positive polarity will be here because now current is coming out of this terminal. So this will be the positive polarity. Okay. So now where does the dot convention come into picture? Now we have understood that the sense of winding will decide the polarity. Now what happens is the sense of winding, we will not always know the sense of winding. Okay. When we have a machine, let us say we are taking a transformer, the windings will not actually be visible to us. What is going to be visible to us is that this entire structure will be covered, only these terminals will come out. So in that sense, how will you find out which one will be the positive polarity when you give the current in a certain direction? So that is where the dot convention comes into picture. First you write this statement, then I will explain to you. If a current enters dotted terminal of one coil, the reference polarity of mutual voltage in second coil is positive at dotted terminal of second coil. Another way in which you can write this is, so here we have taken current entering. So if you take the other way round, if current leaves a dotted terminal of one coil, then polarity of mutual voltage in second coil is negative at dotted terminal of second coil. So now we will understand what this is. We will take the first coil, the second coil. The sense of winding now is not known. What is instead known is the dot polarity. So for this winding, the dot polarity is given here. For this winding, the dot polarity is given here. Now here, let us say the current is entering through this terminal. So now the current is entering the dotted terminal of this coil. What is the statement here? If current enters dotted terminal of one coil, then the reference polarity of mutual voltage in the second coil is positive at dotted terminal. So that means I enters dotted terminal, then this dotted terminal will be positive. So here you will have a positive polarity. As simple as that. Now you don't have to worry about the sense of winding. What is the sense of winding? Then what will be the current that should flow? And according to the current, what will be the polarity? You don't have to worry about it. Okay. When the dotted polarities are given, then you can directly get the polarity. So the direction of current will now be what? It will flow out of the positive polarity. So why it is flowing out of the positive polarity? Because the coil is now acting like a source. It is now driving the current. Okay. So now if you take another example. For the same coil, we'll now take the current directions to be different. So that means dotted polarity is also here. Now the direction of current we will take to be flowing out of the dotted terminal. So here we come to the second statement. If current leaves the dotted terminal of one coil, then polarity of mutual voltage in second coil is negative at dotted terminal. So the dotted terminal for the second coil is here. So this will now become negative. So if current is entering at dotted terminal, the other side dotted terminal will become positive, otherwise it will become negative. Okay. You can take another example where now we can change the polarities, the dotted polarities. So let us see, this is the dotted terminal and this is the dotted terminal. Then what will happen if the current I flows through this? Then positive polarity will be at the dotted terminal. Okay. Similarly, for the same, or we can take a different polarity. Let us say the dotted terminal is here and this is here. Now the current direction if you take to be in this direction. Now what is happening? The current is entering the non-dotted terminal. That means it is leaving the dotted terminal. So what will happen to the dotted terminal on the other side? It will become negative polarity. So this is the significance of the dot convention. We'll now learn to write the equations for magnetically coupled circuits. So let us consider the two coils to be like this. We are now using the dotted convention. So here there is a dot and here there is a dot. Okay. And the mutual inductance is given by M. This coil self-inductance is L1. This coil self-inductance is L2. Okay. So now the current's direction is also given. I1 is flowing like this, I2 is flowing like this. That means both of these currents are being driven by some external sources. Okay. So now what will be the voltage that will be induced across this coil and also across this coil, because now current is flowing through both the coils, right? So because of I1, voltage will be induced across coil 1 as well as coil 2. Similarly, I2, because of I2, voltage will be induced in this coil because of self-inductance, and through this coil because of mutual inductance. So this voltage if you take as V1, then V1 is equal to what will be the voltage induced because of current through its own coil. Okay, so that will be because of inductance. Now you can see that the current is flowing into the positive terminal. For an inductor, forget about the mutual inductance. For a normal inductor, when the current is flowing into the positive polarity, what will be the polarity here? It will be positive. So L1 di1 by dt. Okay, then what about the mutually induced voltage? Now the current is flowing through the dotted terminal into the dotted terminal. So the polarity here will be positive. Okay, and we have taken the V1 polarity to be positive here. So that means you can add plus M di2 by dt. When you're talking about mutual inductance, it will be the current through the other coil. Now the same circuit, we will, instead of taking the polarity to be in this way, we will reverse the polarity. Okay, so that means here you are taking negative, here you are taking positive. This is now V1. Okay, so V1 will be negative of this, that we know, but we will write with respect to this. So you can see that V1 is equal to, now the current is flowing into the negative polarity. So for an inductor, when current is flowing into the negative polarity, we write as negative. So minus L1 di1 by dt. And here this I2 is entering this dotted terminal, so positive will be formed here, but we have taken the reference positive to be here. So we write the negative sign, minus M di2 by dt. So we have written this equation using the polarities here, okay, dotted polarity and the positive and negative polarities. But you can verify from this itself that should be the negative of it, because we have just reversed the polarities. So this has indeed come negative. So this is the correct expression. Okay. So these are just examples. We will take another example. Here the coils dotted polarity we will change. Okay. So for this dotted polarity is here, for this the dot polarity is here. Current direction, let us say I1 is flowing like this and I2 is flowing like this. Then what will be the induced voltage across this? Okay. So V1 is equal to the self inductances, we will write L1, L2, and mutual inductance we will write as M. Okay. So now what will be the voltage induced V1, which is because of self inductance? I1 is flowing through the positive polarity. So you can simply write plus L1 di1 by dt. Now the current here, it is flowing out of the non-dotted terminal, that means it is entering the dotted terminal. So this polarity, this dotted polarity, it will become positive. So we have plus M di2 by dt. Okay, so I hope this is clear to you. The voltage induced across the coil, it will be the sum, both these voltages will be present. Because of self inductance also there will be a voltage induced, because of mutual inductance also there will be a voltage induced. Okay, so if you take this coil, let us say the first coil, you can actually write the induced voltages in this manner. This will be the self induced voltage and this will be the mutually induced voltage. So the voltage across the coil will be the sum of both of them. The polarities of both of them will be dependent on the dot convention and the polarity into which the current is flowing. Now we have seen a series connection of inductance. If it is series connection, then what will be the equivalent inductance? L1 plus L2. We have not considered the mutual inductance. So now what if there is a mutual inductance? Okay, so let us take the dot polarities like this. Say a current I is flowing like this. Okay, now the induced voltages you can take as plus V1 plus V2 and the total voltage we can take as V. So you can now write V is equal to L equivalent di by dt. We now need to find out this L equivalent. Okay, so we have to find out the individual voltages. What is V1? Now since the current is flowing into the positive polarity of V1, the self inductance you can write positive, so L1 di by dt. What about the mutually induced voltage? This coil, the current is entering the positive polarity, entering the dotted terminal. So what will happen to this dotted terminal? It will become positive, right? So you will have plus M di by dt, since it is the same current that is flowing into the second coil as well. Similarly, V2 will be what? The current is entering the positive polarity. So the self inductance is positive, L2 di by dt, and the mutual inductance also, current is entering the dotted terminal. So here dotted terminal will become positive, which is what we have taken V2 as well. So this will become plus M di by dt. So what will be V? This is by KVL. V is equal to V1 plus V2. So you're going to get L equivalent di by dt is equal to L1 plus M di by dt plus L2 plus M di by dt. Okay. So di by dt will be cancelled and you're going to get L equivalent is equal to L1 plus L2 plus 2 times M. Okay. So this is the equivalent inductance for the inductors when the dot polarity is like this. Now what if dot polarity is reversed? So this is case 1. This is additive connection. This is called as additive connection. Now the second case is a differential connection. So what is going to happen here? The two inductors are going to have dot polarities in this manner. Okay. So what is happening now? If a current flows like this, through one terminal it is flowing into the dotted terminal, and through the other coil it is flowing out of the dotted terminal, right? So this is why it is called as a differential connection. This is case 2, differential connection. So here what will be the equivalent inductance? In a similar manner you can take, this is V, each of the individual voltages you can take as V1 and V2. And what about the self inductance? The self inductance is L1, L2, and the mutual inductance you can take as M. So what will be V? V is equal to L equivalent di by dt. V1 you can write as self induced voltage will be positive, L1 di by dt. What about the other mutual induced voltage? It will be negative. So why is that the case? The current through the second coil, it is leaving the dotted polarity. So here the dotted polarity will become negative. But here we have taken a positive polarity. So it will be negative, minus M di by dt. In a similar manner, V2 also you will get L2 di by dt minus M di by dt. So the final equivalent inductance, if you will get by KVL, V is equal to V1 plus V2 if you do, then you will get the result L equivalent is equal to L1 plus L2 minus 2 times M. So this is the expression for a differential connection. So you have to be careful whenever you are writing the equivalent impedance when there is a mutual inductance as well. Now what about for the case of parallel connection? Here also you will have two kinds of connection, right? So if this is the inductors in parallel, L1 and L2 are the self inductances, then the dot connection will be like this for the first case. Now the currents through each of them are I1 and I2, and the total current let us take as I. What about the voltage? Voltage we can take as V. Okay. So now how will we represent I in terms of V? We can write as 1 by L equivalent integral V dt. Okay. So we are considering this entire combination as L equivalent. Let us now consider each of the individual inductors. Now the voltage V is same across each of the inductors. Okay. Now across this inductor, what will be the induced voltages? One voltage will be because of I1, another voltage will be because of I2. So what will you get? V is equal to L1 d I1 by dt because of self inductance. So the current is flowing into the positive polarity, so we are taking plus. Now the I2 current is flowing into the dotted polarity, so dotted polarity should be positive here. The same thing we have taken positive, right? So here we can write plus M d I2 by dt. Okay, so this is one equation, this is the second equation. Finally, the voltage across the second inductor is going to be similarly L2 d I2 by dt plus M d I1 by dt. Okay, so because of the current through itself and the current through the other inductor. What is another equation that we have? The KCL gives you I is equal to I1 plus I2. This is the fourth equation. Now using these four equations, you can get the L equivalent in terms of L1, L2 and M. Okay, so the derivation is pretty big, so I will not be doing the derivation here. I will write the final result. L equivalent, you are going to get L1, L2 minus M square divided by L1 plus L2 minus 2M. This is for this case. Okay, what is the other condition? Other case, you will have two inductors, but now the dot convention is going to be like this. Okay, so now the mutual inductance is between these two. Now L1, L2, if you take the self inductances, then L equivalent, you are going to get L1, L2 minus M square, the numerator will be the same, divided by L1 plus L2 plus 2M. So this is the equivalent inductance for this case. Okay, so this is the differential case and the previous one was the additive case. Okay, now you can see that the numerator is same, but in the denominator here you have L1 plus L2 minus 2M. Here you have L1 plus L2 plus 2M. So which one will be more? Here the denominator, this denominator is high, so this equivalent inductance will be lesser than this equivalent impedance. So you have to remember that differential inductance will always be lesser. So since this is coming in the denominator, here you get plus sign. Whereas in the case of the series inductor, this term was in the numerator. So there for the additive connection, we got L1 plus L2 plus 2M. Okay. So I am just telling this so that it will be easier for you to remember the difference between the series and parallel connection as well as the additive and the differential connections.